Bouncing? Did I hit the, okay. I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So I'm going to cover the wave equation today. So let's get into it. Try to leave some time at the end of class for questions about the test, all right? So let me set an alarm so I remind myself to stop talking about partial differential equations at some point. Let's see here. There we go. Wait a minute. When do we end? 12:30. All right. 12. Nice. So, in chapter 10, there's a couple of sections on Fourier series. All right. And if you read, there's a Fourier cosine series and there's a Fourier sine series. These are both developed for the interval 0 to t in section 10.4, and there's particular formulas for those, and you should look at that and read it for yourself as you're working on the problems that I'll eventually give you for these. And then there's the so-called full Fourier series, which involves sine and cosine, and it's for going from like minus t to t. So there's like three competing popular Fourier series ideas. The one is on a symmetric interval about the origin going from like minus something to plus that same thing. That's one, I call that the full Fourier series. That involves sines and cosines, all right? And then again, there's the cosine series or just the sine series that's just defined on 0 to t. So which one of those three we want to use depends on the problem at hand and in the context, all right? And there's an interplay between these three different kinds of Fourier series, but my focus in here is just going to be on solving problems as opposed to, expositing the theory. And there is much to say about the sorry, I'm looking for a problem here to solve. Fourier series in the abstract. I mean, the theory of Fourier series is very interesting and rich, but we'll have to leave that for another course for the most part. So, a course which we don't currently offer, but setting that aside. I on occasion have taught a special topics course for you guys that's been on deeper Fourier series. Well, just once really. So I can tell you some things to read if you're interested. Let's try to solve a problem in here. This looks like a good one. I'll look at number 3 from section 10.6. So this is on the wave equation. I won't take time to derive the wave equation this semester. It's a simple matter to do it. You can apply Newton's second law to a little segment of string, and you can derive the wave equation from just an application of Newton's second law. If you watch like last year's lectures, you'll see it. It's about 10 minutes or so. But I want to spend that time on review for the test today. So, and I think it's important for me to do this example today. So if you want to do the PDE project over break, you can. That's why I'm doing this today, as opposed to spending the whole time on test review. I think it's in the big scheme of things, you're better off if you want to do the PDE project over break, so that you're not fussing with that after break in the midst of your engineering projects or whatever. All right. So you're like, well, are you going to post the PDE project? PDE project, aka Quiz 5. All right, that's going to be the PDE part of the course. That is not, so PDEs are not on the test. I should tell you that much, right? I mean, test what? Oh, test 2. We haven't test. Is it test 2 or test 3 in here? Just 2. Oh, that's right, because we're on Tuesday. We're on Tuesday, Thursday, yeah. So we have 2 tests and then 5 quizzes and what else? Okay, so here it is. Partial squared u partial t squared equal to 4 partial squared u partial x squared. Now, at least try to explain what this is talking about momentarily. Here, 0 less than x less than pi, and t is positive. we're also told that u of 0t is equal to u of pi t is equal to 0 for t greater than 0. We're told that u of x comma 0 is equal to x squared times pi minus x, all right, for 0 less than x less than pi. And finally, we're told that partial u partial t of x comma 0 is equal to 0 for 0 less than x less than pi. So this is problem number 3 from section 10.6 in Nagel, Saff, and Snyder's Fundamental of Differential Equations. This happens to be the 6th edition I'm holding, but I would wager that this problem is in lots of other editions. Let me explain what we're looking at. So this equation, which I'll box in red here, is the wave equation. And what it describes is it models transverse waves on string. So here we're talking about, the picture is something like this. This is u, this is x, right? So the solution should look something like, I don't know. Well, this solution has what? U of 0 is 0, right? U of pi is 0. And so we're kind of stuck with that. That's given, right? This boundary condition is given. U of 0t and u of pi t is 0 for all t. So what that's saying is we're looking at a string where the endpoints are fixed, like that, all right? So fixed endpoints. And what's this business? U of x0 is x squared times pi minus x. What's that mean? Well, it's got a 0 at 0, right? And it's got a 0 at pi. And so I guess that looks something like it's bouncing off 0, right? So, I mean, I'm not sure exactly what that looks like, but it's something like, right? I'm not sure exactly what it looks like. I mean, if I were to continue that graph past 0 and pi, it bounces off 0, right? It's got a 0 of order 2 at 0, but it's got a 0 of order 1 at pi. It's crossing through the x-axis there. So they're different, the nature of the zeros at the endpoints. But that's just a snapshot at time 0, right? And what's this say? This says that so this is initial position. This is the initial position of the string, right? And what's this? This is the initial velocity of the string. So it's saying basically we're taking the string and shaping it into this waveform and then essentially plucking it, just letting it go from there. And then after that, it's going to wave freely, all right? And we're going to find what that motion looks like, right? That's what we're going to solve. We're going to solve this wave equation to see what would happen if you plucked a string with this shape and then let it go, right? We're going to do the math and figure out what that looks like. So this would be the mathematics to describe, for example, like a guitar string, right? If you had a guitar string, it's fixed at 2 endpoints. You pluck it, and then it's going to have waves on it, that sort of thing. So of course, waves on a string are interesting for the sake of musical instruments and other things. I guess this is probably a simplistic model. There's probably a little bit more to those, involving resonance with the cavity of the wood and so forth and on. But all right, so how are we going to solve this? So if you remember last class, we went through a procedure which was what? Let me remind you the game plan for last time. What was it? So one was to separate variables, right? Two was to interpret boundary conditions. Three was to form a formal solution. So interpret boundary conditions, and then that says that implies countable family of solutions, say UN of Tx in this case, right? So we're not going to find just one solution that fits the boundary conditions. We're going to find a truckload of them, and they're going to depend on some integer n. That's what's going to happen. Then we're going to form a formal solution by taking a series of these solutions, right? And then step 4 is going to be to use initial data and Fourier technique to draft final solution. So, what is this Fourier technique I'm talking about? The Fourier technique, but when I say Fourier technique, what I'm saying is that I can take this, and the Fourier technique says Fourier technique allows us to expand this as sum of trigonometric functions. Now, which trig functions we should expand that as will become more apparent as we work on this problem. I think we want a sine series for this one. But let's, we'll come back to what I just wrote in green, all right? So let's start with number 1. So, if I ask about something PDE-wise on the final, I tend to focus on 2 aspects of this discussion. The one is going through and solving a boundary value problem, like we did at the start of last class, right? So that makes a decent final exam question, right? Because essentially, the things we did at the start of last class, what are they? They're nothing more than the first part of the course with a little bit of, extra logic involved. Then the other thing that's an appropriate final exam question is this step 1, the separation of variables part, right? Like setting up the formal solution. That is something that we should be able to work through by hand. So let's do it. Let's do it. So we're looking at, let me say u tt equals to 4 uxx. That 4 is where's the 4 coming from? The 4 has to do with the tension of the string. Right? If you change the tension of the string, it will make waves behave differently, right? So that's a, that would come from the physical analysis that I'm skipping today. But anyway, 4 uxx. And so what we're going to do is we're going to let u of x comma t equal to x of x times t of t, right? So u tt is going to be x t prime prime, and uxx is equal to x prime prime t, just like we did last time for the heat equation, right? Where the primes on the factors in the product solution mean ordinary derivatives, either with respect to time or space as appropriate. So then we plug those in, plug in. That gives us x t prime prime equals to 4 x prime prime t. then divide by xt to obtain t prime prime over t equals to 4. And I think I'm going to put that 4 with the t. I'm going to put that 4 over with the t. T prime prime over 4t equal to x prime prime over x, yeah? You could put the 4 somewhere, or the I'm going to put it with the t to make my life easier. And then again, we get to that same, fork in the road we got to last time, which is on the left-hand side, we have a function of time. On the right-hand side, we've got a function of space. So it must be that the only thing in common with space and time, them being independent, is just a constant. So we can set this equal to minus a k. Why set this equal to minus k? Again, to make use of my 4-part proposition that I gave you last time, right? So hence, we face, what do we face? We face x prime prime plus kx equals to 0, and t prime prime plus 4kt equal to 0. So there you go. This is, I've taken my separation of variables, and I've traded a given PDE for a pair of ODEs in the product solutions. So that's step 1 is done. Step 1 is done. Step 2. So now we're going to use the boundary conditions. These are fixed endpoint boundary conditions. So our boundary condition is that u of 0t equal to 0, and u of, what was it? Pi t equal to 0. All right, so what's that say? That says that x of 0, right, t of t equal to 0, and this tells me that x of pi, t of t, equals to 0. These are both for, for t greater than 0. So thus, x of 0 must be 0, and x of pi must be equal to 0. So the boundary conditions transfer to the spatial part, the spatial solution, right? So essentially, and oh look, now we're back to the first thing we looked at last class, right? Again, fixed endpoints being 0, and what did we determine? This is a boundary. What did we learn about this problem? What does k have to be? So we're facing x of 0 is 0, x of pi is 0, and x prime prime plus x equal, x prime prime plus kx equal to 0. What was the solution to this boundary value problem? Right, by the first proposition from last time, we learned what? That k was equal to, what was it? N squared pi squared over L squared, which here is just n squared since L is equal to pi in this problem, right? We solved the boundary value problem from 0 to L, but here L is pi. And what was the solution where x sub n is equal to the sine of n pi x over L, which of course here is just the sine of nx. So now that we recall that, we can attend to our temporal solution now, right? We can take care of the time problem. So what is that? We've got t prime prime. What's my k equal to? K was what? N squared, right? So t prime prime plus 4n squared t equal to 0. What does that say about was my, so this says that lambda squared plus 4n squared is equal to 0. So lambda is equal to plus or minus 2i, and that gives me tn is equal to something like, I don't know, an cosine nt, oh wait a minute, cosine 2nt, right? Plus bn sine 2nt. Something like that would be my temporal solution. So put it together, what's that make my un of xt look like? It's got a few different moving parts, but it looks something like this. Un of xt looks like an cosine of 2nt sine nx plus bn sine of 2nt sine nx. So what I did there, guys, is I multiplied my t and my x for the allowed k, which is equal to n squared. So this completes part 2. Part 2 is now done. Part 3 is actually pretty simple. So now we just got to take the sum, n equals 1 to infinity. There you go. The sum n equals 1 to infinity of what I wrote in purple, and that will be our formal solution. All right, so here we go. U of xt equals to the sum n equals 1 to infinity of a sub n cosine of 2nt sine of nx plus bn sine of 2nt sine of nx. So this is step 3. Not much to step 3, but there it is. All right. I should emphasize this summation is going over all of that. What's my next? Now I got to use the initial data and the Fourier technique to, basically what we're going to do is we're going to use the initial data and the Fourier technique to tell us how to select a sub n and b sub n to form the solution to the problem. So let's get started on that. What was my initial data? U of, what was it? X comma 0 equal to x squared times pi minus x, is that right? Yeah. And that's going to be equal to, I need to give this thing a name. Let me call it Pac-Man. So this has to be equal to Pac-Man eating what? T equals to 0, right? So what happens when you feed t equal to 0 into this Pac-Man? I get sum n equals 1 to infinity of what? What's the sine of, plug in 0 into the sine 2nt, what'd you get? You got 0, right? So the bn term is gone. But the an term, what's cosine of 0? It's 1, right? So we've just got an sine nx. So the technique of Fourier says, oh, fine. I can find this. I can find my a sub n's. I just need to take the x squared times pi minus x and convert it to an infinite sum of sines. And everybody knows how to take x squared times pi minus x and convert it into an infinite series of sine functions, right? Because that's just something you already know. Not really, right? We need to figure that out. But yeah, sure. The technique we're going to use is the same I used last time, which is just to, I mean, there's two different ways you can go here. You can consult the book and go, hey, there's a theorem in the book which says, if I want to rewrite this thing, let's call it f of x. You know, we could consult the textbook and we could say, well, that's f of x. I want to write it as a sine series. I go to the textbook. I go, all right, this is a sine series on 0 to pi, right? So I look in my textbook. Now, I did it kind of, I did it from scratch last time, right? I just integrated both sides of the equation after multiplying it by sine, or cosine, I think it was. So, you know what, this time I'll use the theorem from the book just to be a little bit more equitable. And this is from, well, this is actually a definition on page 609. He tells us, here's I'll call it a theorem, the sine series theorem. And what the theorem says is that f of x on 0 less than or equal to x less than or equal to t can be expressed as the sum n equals 1 to infinity, and the notation in the book is little b sub n, sine of n pi x over t, all right, where the Fourier coefficient, b sub n, is equal to 2 over t, the integral from 0 to t, f of x sine of n pi x over t dx. So we need to make some adjustments, right? I have used in the past class, I did not use big T, I used what? I used L. So I was thinking of L playing the role of T in the book, right? But let's just adapt the sine series theorem to our current problem. What do we have? We have that f of x equals to x squared times pi minus x is equal to a sum n equals 1 to infinity of b sub n sine nx, right? Where bn is 2 over pi, integral from 0 to pi, of, well, x squared times pi minus x times the sine of nx dx. Does that make sense? You're like, what doesn't make sense is you're asking me to do this integral, right? So, I'm not a monster. Like, you know, for quiz 5, when you get to the integral like this, you're welcome to use Mathematica or, you know, some computer algebra system to actually solve these integrals. But I'd like you to think about them carefully and try to simplify the answer as much as possible. Like the one I did last class, I just kind of left, I mean, we kind of got to the end of it at the end of class, but if you actually look at the formula I wrote last class, you could simplify that considerably because it's 0 for even values. Like you have -1 to the n, -1, So like if n is even, it gives you 1 minus 1, I think. So actually, we could have simplified that answer just to be a sum of odd terms, I think. That's the kind of simplification I'd like to see from you guys in the answer for the quiz 5. It doesn't really matter to me that much that you actually do, you know, brute force battle with the integration by parts here, right? I mean, it's good for you to do that if you're a math major. But, you know, so what I'm trying to say is you can sort of phone a friend when it comes to the calculation of the Fourier integral. Yeah.
As far as whatever this would end up on the final, supposedly, how do you
Well, I think you guys can do the integral we came to in the last class. But we have many other fish to fry, so to speak, on the final. Like, I would be surprised if I actually asked you to calculate the Fourier coefficients in the final. You know, you'll be busy with, you know, factoring polynomials and finding eigenvectors and taking Laplace transforms, finding series. Like that's will take all of your time. I think there's no time for Fourier coefficient calculation in a 2-hour final. You know, if we had a 3-hour final. But anyway, why don't we have 3-hour finals? But anyway, I digress. Because what?
Because some classes have finals that take 20 minutes.
But it's bad for you guys not to have 3-hour finals. You know, many of you are taking professional exams, which have a length which is more like 3 hours. If you always have 3-hour finals in all your classes, it builds up a certain endurance that makes you much better at those kinds of tests when you later take them. Always having 2-hour finals is very disadvantageous to you long term as test takers. Just a thought, but whatever. We can have a shorter final exam week with 2-hour finals, so yay. All right, so 2 over pi. And this would be, oh man, you guys can make me think. Yay. Tell you what, I'm going to go ahead and use my computer to do that because we're otherwise going to be cramped for time. Because it'll take me 10 minutes to. Oh, fine. I guess it's. I guess. Fine. All right. It's about the same. 2 pi. And let's see here. So I'll make this my u, make this my dv. So I get 2 over pi x squared minus x cubed times minus cosine nx over n, right? You got to evaluate that thing from 0 to pi. And then we've got to do plus the integral of cosine nx over n times 2 pi x minus 3x squared dx from 0 to pi. So then I will make this my u and that I'll make my u2 and my dv2. So that will give me 2 over pi. Let's see, if I evaluate this from, let me just take care of that. What happens, I plug in 0, I got 0. If I plug in pi, what's cosine of n pi? That's minus 1 to the n, but I've got a minus, so I get minus 1 to the n plus 1 over n times pi cubed minus, what? Cool. This dies. When you plug in pi, you get pi cubed minus pi cubed. This actually is just, it's gone. This whole first piece zeroes out. Let me just erase that. That's nice. So I have 2 over pi. And let's see here. So that is, what do we got? 2 pi x That's you. Minus 3x squared. What's the integral of cosine nx over n? That is sine nx over n squared. Still got to evaluate this thing from 0 to pi. Huh. Well, that's 0. Cool. Minus the integral of sine nx over n squared times 2 pi minus 6x dx from 0 to pi. Now, the 2 pi over n squared times sine x term, well, that, all right, so this piece is all 0 again. 2 over pi. I've got 2 pi over n squared. Well, 2 pi over n cubed, actually. 2 pi over n cubed times minus cosine of nx evaluated from 0 to pi. I'm just integrating the first piece. And then minus 6 integral from 0 to pi. Well, excuse me, 6 over n squared, I should say. 6 over n squared x sine nx dx. Does that first one evaluate to... I think the first one lives. So it looks like I've got a 4 over n cubed times 1 minus 1 to the n, because cosine of n pi is minus 1 to the n. And I flipped it because you got to minus the cosine 0, which gives me a 1 minus 1 to the n. And then this piece over here, I need to integrate by parts. So let's call that dv3, and I'll call that u3. So I get minus 6 over n squared times x minus cosine of nx over n rather, evaluated from 0 to pi, plus the integral from 0 to pi of, goodness gracious, cosine, why didn't I use Wolfram alpha for this? I'm an idiot. Cosine nx over n dx. But the last integral dies because that integrates to a sine, and then sine is 0 at 0 and pi. And so this one can contribute, though. That one gives me 0 from the lower bound, and so it looks like I'm going to get 4 over n cubed, 1 minus 1 to the n, minus 6 pi over n squared, n cubed rather, times minus 1 to the n. Yep. So let me collect that all together. I've got b sub n equals to let's see here. If n is even, that first term with the 4 is gone. And the second term is just minus 6 pi over 2k quantity cubed. On the other hand, if n is odd, so if n is equal to 2k 2k plus 2k minus 1 rather, then that makes me get an 8 over 2k minus 1 cubed from the first term, and plus 6 pi over, the same, so 8 plus 6 pi. 8 plus 6 pi over that, I think, because if n is odd, minus 1 to the n is minus, so I get minus minus, which is a plus 6 pi over n cubed. And that initial term becomes 1 minus a minus 1, which is 2. 2 times 4 is 8. So this is what I calculate. Now, is it possible I've made a mistake? Yeah, sure. But this is how you do it if you don't have Wolfram Alpha or Mathematica to check yourself, right? Well, even then, they might not quite refine the answer. Like, they might give you something that you still need to kind of like tinker with, right? Okay, great. So that means I can take these and plug them up in there, and then what? So what I'm trying to say is I'm going to come back to, I'm going to erase part 1 and start writing there. I could write on the sideboard, but I don't like the way it shows up, so and those chairs are in the way. Actually, I think we don't need, I just need 3 and afterwards at this point. Stuff from before then won't really matter to us. I don't think. All right, so start here. We just figured out that x squared times pi minus x can be written as the sum k equals 1 to infinity, right, of, bless you, 8 over 6 pi, 8 plus 6 pi over 2k minus 1 cubed times the what? I'm doing the odd terms first. So b sub n sine of nx, but what's n here? Sine n is 2k minus 1, so it's 2k minus 1 x. And then plus the sum. I'll do a j instead of a k this time, all right? J equals 1 to infinity of, let's see here, I've converted my k to a j. So I've got myself a minus 6 pi over 2j. 2j quantity squared, or is it cubed? Cubed, okay, thanks. Cubed. And then the sine of 2j x. All right, this is the Fourier technique. I have written my initial condition as a sum of sines. There it is. That's the Fourier technique. Now, it's a simple, once you've done that, it's not hard to figure out what my a sub n has to be, right? Because this is equal to the sum n equals 1 to infinity, right, of a sub n sine nx, right? Which I could rewrite as the sum k equals 1 to infinity of a sub 2k minus 1 sine of 2k minus 1x plus the sum j equals 1 to infinity of a sub 2j sine of 2jx. I mean, you don't really need to even make this step. I'm just making it so it's kind of more in your face what I'm doing. I'm going to match coefficients of matching signs, right? I've either got evens or odds. You've got to match the evens to the evens, got to match the odds to the odds. And so what's this tell me? A sub 2k minus 1 is what? Apparently 8 plus 6 pi over 2k minus 1 cubed, yeah? And how about my a sub 2j, my even a's? I got minus 6 pi over 2j cubed, right? Which, of course, we could be civilized human beings and rewrite as minus 6 pi over 8j cubed, otherwise known as minus 3 pi over 4j cubed, yeah? Probably should make that simplification so people don't laugh at us. Or maybe just because it's the right thing to do, right? You know, mathematical integrity is doing the right thing even when people aren't looking. also true about ordinary integrity? No? This has not been said in convocation this year yet? Surely it has been said by now. All right, I digress. Great. So what have we not used? Initial velocity, no! Right? No, not the initial velocity. But now we return to 3, and differentiate. And what's partial u partial t equal to? Looks like we got a minus 2n a sub n sine of 2nt, right? Sine nx plus 2n b sub n cosine of 2nt sine nx. Now, what did, oh, thankfully, I am so thankful to see that 0 there. Aren't you? Partial u partial t at x comma 0 is equal to 0, and it's also equal to, well, plug in 0 here, what do you get? When plug in times 0, what happens to that? Well, the a sub n's are gone, but that doesn't bother us. We already know what those are. We already fit the a sub n's with the initial position in the Fourier technique, right? How about the b sub n's, though? This gives us what? Sum n equals 1 to infinity of 2n bn sine nx, right? Which tells me that my bn is equal to 0 for all n. Oh, that is a relief. So what would have happened? What would have happened here if we had been given a non-trivial initial velocity? What we would need to do at this juncture in the solution? We would need to apply the Fourier technique to the initial velocity and expand the initial velocity profile to match, to choose the appropriate b sub n's. Thankfully, that did not happen, right? So at this point, we're done. All we got to do is put the pieces together, and that's it. So what do we got? We have that u of x comma t equal to, I'll write it in terms of the k and j. Sum k equals 1 to infinity of 8 plus 6 pi over, I hope I haven't made a mistake. I mean, it's possible, guys, but I hope the spirit of the solution shines through if the details are off here. 8, 6 pi over 3, and that's my cosine of 2 times 2k minus 1 t sine of 2k minus 1 x. All right, and then plus the sum j equals 1 to infinity of, I should put a minus, I'll pull the minus out, minus the sum j equals 1 to infinity of 3 pi over 4j cubed cosine of 4jt sine of 2jx. And there you go. That is the solution to this problem. Now, if you want to make one of these friendly so that you could solve it like on an in-class test, how do you change the problem? What do you do? It's pretty simple. what you do is you give an initial velocity and an initial position, which are already a Fourier series. See, this problem gets radically easier if, instead of giving this horrible initial position, which is written in terms of a polynomial, right? If instead of this, if I had written like, you know, sine of x plus the sine of 3x here, right? If I had instead have written, if u of x0 was, you know, sine of x plus, let's say, 13 sine of 7x, that would have told me that I should make a1 equals to 1, a7 equals to 13, and a sub n equal to 0 otherwise. Right? In that case, the solution would just be what? Assuming initial velocities being 0 as well, right? Then the solution would just be u of xt equals to, what you got? You got cosine of 2t sine x plus 13 cosine of 26, wait a minute. Uh-oh. I just change this eventually. Tired of this one. Let's see here. Let's see here. Cosine. Where was I? N equals 7. So 2 times 7 is 14. 14t sine of 7x, right? So that would be the solution for the purple initial condition. See, these don't have to be horrible, but I wanted to show you the full example to start with, right? You see the difference. Like what I wrote in purple makes a decent test question. What I wrote in red, where you actually have to straight up calculate the Fourier coefficients, goodness gracious, that's just not friendly for an in-class test, yeah. The only way I know to make it friendly for an in-class test is to tell you the Fourier coefficient integrals. But then that kind of tells you what the answer to the problem is. So it's kind of a catch-22, you know? You're like, I don't see the problem with telling us the answers, right? No? No? I think if I offered the 201, I said, you know, I'm going to give you a test. I'll write the answers on it for you, you know, and hand it out. They'd be like, okay. They'd still write something on it, though, I feel like. So I'd still have to grade it. I don't know. Hopefully not. You might be wondering what's on my laptop. I guess, I don't know if you've noticed this or not, but I have certain figures, right? So, over here, see the hand-drawn ones. These are lightning warriors. I'm not sure what that means, but it's something my children play, and so they drew a couple for me, and I said, oh, I'll put it on the laptop. So I feel like I should explain at some point. I don't know what a lightning warrior is exactly, but it's one of the many reasons that they hit each other with sticks for. So. All right. See, when I was an undergraduate, and I got to the class where we solved these kind of differential equations, I felt like I'd really accomplished something. You know, I finished a homework problem. I looked back at my work, and I had 3 pages of calculations for one problem. I felt like, you know, that's a problem, right? And there's a sense of accomplishment when you get to the end of one of these PDE problems because they're just so much longer than anything else you faced, right? And the funny thing is, they get worse. I mean, if you do ones with inhomogeneous boundary conditions, there's like a whole other toolkit that you have to develop for those. If you solve problems that are not over whatchamacallit, not over Cartesian domains, but like over a polar coordinates, when you do the separation of variables, what ends up happening is you come to Cauchy-Euler problems in the radius when you look at the product of the R solution and the theta solution. So there's a lot more out there that we don't actually touch on in here too much. But all right, well, let's see here. What would you like me to look at? I mean, I can look at test. We want to look at test 2 from last year. Would that suit your fancy? Is that something we say? I don't know. I think that's so like 100 years ago. Let's see here. What, test 2? Test 2, right? Look at this. Oh, the first one. Let's see here. And I think, let me just check on this right quick, but I believe the organization of this semester is pretty much the same, right? A little bit different, but so what's on test 2? Series solutions, singular points, Cauchy-Euler, systems, eigenvectors, the generalized eigenvectors, the complex eigenvectors, possibly energy analysis, which was the diagrams you just turned in, Laplace transforms, of course, the unit step function stuff, the direct delta function stuff, and that's it. Now, as I said on there, it does not cover 1113 material. It also does not cover 11.8 material because we got ahead, right? So 11.8 and 1113 were both PDEs not on your test 2. Like I was trying to explain today, it's possible that there's like 10% on the final, which is about the non-integrative part of the PDE solution, right? The part that's not the horrible integration by parts like I did today. Anyway, so getting back to test 2. Let's see what we got here. I don't think so. Would you like me to post it for you guys in Blackboard? I can do that. Oh, let's look at the solution. Yeah. Since our time is limited here. All right, so first one's a system, right? And I think I said to solve by the method of eigenvectors and, oh, you're fine, thanks, you already had it. Solve by using matrix methods, all right? So convert it to a matrix problem, find the characteristic equation, eigenvalues 3 and 7, look at a minus 3i and a minus 7i, and then I just eyeball it and go, wait a minute, that's perpendicular to both of the rows, that one's perpendicular to both of these rows, so them's my eigenvectors, and then bam, solve. So that's the eigen solution. Ooh. See, I can't plug it in up here because this isn't actually connected. So I have to pretty much do this, or I won't reach over there. I guess there's a bonus. If I do actually snag my computer and knock it to the floor, you guys will be happy. It's going to be hilarious. Bad people. Let's see here. You'd laugh at it. Jerks. Let's see here. Okay, so this one works out to be complex. So we find one complex eigenvector. And from that, we find the real and the imaginary part and construct the solution by the standard technique. This is the real part. That's the imaginary part of the